Welcome everyone. Good afternoon. A lot of more people than I have expected. Doesn't make me less nervous. I will show you the slides. They are more interesting than a picture of me. Today I will give you a presentation about how you can write Rust application on top of Zephyr. I'm a huge advocate of Rust ever since I started my first non-trivial applications with it. I see the benefits it brings with it, and it's really a nice language. And I'm an embedded software engineer. That means I also have a lot of resource restricted projects, and on some of them we are running Zephyr now successfully. But up till today we are with C as the programming language of choice. And my idea was to evaluate now, where are we with Rust support on top of Zephyr? Can we use it? What do we have to do? So first of all, thanks to Mohammed for his previous talk here. It was a very good overview. And I was a bit afraid that we have a huge overlap in these two talks. I just saw on yesterday that we have these two talks. But I basically approach the topic from a different perspective. I'm going into an application and show you how the application uses Zephyr. So I won't explain the benefits of Zephyr, but let's start with some benefits of Rust. Why should you choose Rust for an embedded project? And I think the most important point are the safety concepts that Rust brings with it. We have a strong type system, the bounce checker, the ownership model, borrow checker, lifetimes. They all try to minimize memory issues like buffer overflows, use after free, double free, and so forth. So that's basically gone with Rust. Then there are some additional features like the send and sync markers that every data type has, which describe if the data type can be used in a thread-safe way. Send means you can transfer the ownership to another thread safely, and sync means you can access an object from different threads in a thread-safe way. All these features are basically there to move the error detection to compile time, and not experience the problems at runtime, which is not the nicest way for embedded systems because you don't have log files or anything to analyze them. But there are more benefits of using Rust. Rust is a very modern programming languages with concepts from functional programming languages like algebraic data types and pattern matching, if you know them. You have support for async await, which means you can write more efficient IO-bound applications than the threads. And you can have a lot of async tasks compared to OS threads, for example, especially on embedded systems again. But you can also design your application in a different way. You can have an actor-based system where you have tasks as actors, and you communicate between the tasks through channels. So again, you have a thread-safe way by not sharing state, but sharing messages or communicating with messages. And then there are much more patterns like the type state pattern. I see this, for example, in the embedded HAL, where the type describes what you can do. An example, when you acquire a GPIO, for example, it might be uninitialized. So you have a type uninitialized GPIO. Now you configure it to an input. The type of your object changes, and the only functions that you can call in it are the functions that make sense in an input GPIO. Once you reconfigure it to an output, these functions are gone, and you have different functions available. And this is again a huge support because the compiler will detect it, and even your IDE will only propose you the functions that you can call in this time. So I didn't see any type state yet in the support in Rust and Zephyr yet, but there will be something. Yeah, there's one. Cool. Cool. We'll have a look at it. And there are more patterns that are coming with the Rust programming languages. And I think that's why it's a good combination, Zephyr and Rust. They both have a really good tooling around them. In Rust, we have Cargo as the build tool, dependency management tool, basically a tool for everything. It's extensible, you can load plugins into it. We have static analyzing, static code analysis tools like the Rust analyzer and Clippy, unit testing, integration testing, all comes with the tool, as Mohammed already mentioned. Also. So, but how does Rust integrate with Zephyr? So it's a Zephyr first approach, basically. So you control everything with the command line tool Rest. Rest, in the background, uses CMake to build the project. And the Rust code is not compiled just with the Rust compiler and triggered by CMake. No, it's done like every Rust project, or almost every Rust project. It's managed by Cargo. So you have Cargo.toml file describing a project, and this Cargo tool is then called from CMake. So we're using the tools that belong to each environment in each language. And you can do, as we have seen in the demo before, if you have been there, we can do a best build, and then build the Zephyr image, it builds the Cargo application, link them together, and with a flash command, we program it to a device like I will show you later. Rust applications are linked as static libraries. Are linked with static libraries with the Zephyr binary at the end. They have a single entry point called Rust main, and you see here also that it is marked as a C function so that it can be called from the C code. And you have to know that we are at the moment limited to no standard. It means we cannot use the Rust standard library. Means we have, of course, no access to the file system, for example, but also things like network functionality and so forth is not coming from the standard library. But a lot of crates that you can find, crates are libraries in Rust, also support non-standard configuration with a reduced set of features sometimes. So if you want to use a Rust dependencies, for example, for serialization or deserialization, it should not be a problem to add a dependency and specify you want a version without support for the standard library. Now, with this knowledge, we are now able to write our first Rust application. But I call this an isolated Rust application because we cannot interact with Zephyr yet. We cannot interact with some hardware and so forth. The only effect that we can have is heating up the CPU by the ends of these. So let's have a look at what we need to write our application and communicate with something else. So, of course, we have all the functions that Zephyr provides. We have the Zephyr API, and we need we need a language binding that gets generated by pre-built steps. So from the Zephyr API, there's a file generated called bindings.rs, and this basically gives us the C functions that we can call from Rust. There's a pre-built step, which don't know what the correct name is. Let's say it converts the device tree into a device tree.rs and makes the device tree available in Rust. So you can now look for the devices that you have configured in the device tree for your board. For example, on this board I have LEDs, I have switches, and so forth, so that I can address them. And then you might want to have also access to all the options that are configured in kconfig files. I haven't used them in the example yet, but we have a world example for Mohammed and also the examples that you see in the Zephyr Rust project. They are printing, for example, the board name in the Hello World application. And then there is another crate, again, a library in Rust, the Zephyr crate, and this provides also a layer of abstraction on top of Zephyr. Actually, I think it's also using the bindings at the end, but these are then more the Rust-like functions that you have available and not pure C functions. So one problem that I ran into is that Rust basically treats everything outside the Rust ecosystem as unsafe. And actually this is a shared state out there. There's interrupts which are triggered by me, so I'm not deterministic basically from the point of the application. Also, the hardware operating system. So there's a reason why Rust thinks everything outside is unsafe. And if you want to interact with code that is unsafe, you have to put them into a code block which is marked as unsafe in Rust. And that basically turns off all the safety checks that Rust brings you. So we don't want to write a Rust application that starts with the unsafe keyword and ends with the curly bracket at the end. So then we are maybe even worse than where we have been before. So my approach basically would be to have a layer between Zephyr and a business application that handles all the interaction with the hardware, interaction with Zephyr, and provides a safe interface to the business application. This is formally not correct, of course, because what's unsafe is still unsafe. But I can draw this line as a trust boundary and say everything below this line, I have reviewed it, I tested it, and I treat it as safe, so that my business application stays clean, has no unsafe code, and doesn't know too much about the lower layers. So this is the concept that I will show you. And now I want to give you a code walkthrough to an application that I've written. It's basically this countdown that you have seen at the beginning. On this board, I have two hardware switches, which I use to configure. You can see it on this slide. Actually down. So I have two buttons which I can use to configure the start of my countdown. If I press both of them, it's starting the countdown and counting down to 0. Nothing bad will happen here. It's a very simple application, but I try to follow this abstraction, and I will show you how this looks like. So we have the countdown application. Then we have Zephyr at the bottom. And what I'm going to use is I have on one side a thread which is monitoring the two GPIOs for the switches. And I have code that manages the LED matrix. And the LED matrix is a bit tricky because on this board you have basically 5 GPIOs for the rows and 5 GPIOs for the columns. That means you can actually address only one LED at one time. So there must be an application which refreshes the display with a higher frequency and goes pixel by pixel and turns the LEDs off and on. And actually, I think we have seen with the camera flickering, which is basically the concept that we have LEDs that are turned off. So let me go to the source code. Let's start. This is basically my project. It's derived from the Zühlke example of the Zephyr support. And I want to start really from the basics. So this is the CMake file that gets called to trigger some function or a CMake macro that calls cargo. Cargo is, as I said, a build tool from Rust. And cargo will look in the cargo.toml file with the project description. We'll basically find the name of the application. That's important because Zephyr will link with this name. It specifies that we want to produce a static library. We don't want to produce an executable because our Zephyr application will be the executable. And then we can have dependencies. I don't use any dependencies at the moment in my example. So we only use the Zephyr abstraction library and the logging crate. And we also specify here some build dependencies. So there's the Zephyr build, which helps to do all these pre-build steps to create all the language bindings for the IDE. And the single point of entry is in the lib file. That's a convention of Rust that for static libraries you have a lib.rs, and here you find Rust main. So this gets called by Zephyr once I started. And I would like to start with the application. So let's have a look at the application. I said the application has no unsafe code. It doesn't know anything about Zephyr, which is not true in my example. There's one location where you see Zephyr appearing. It's something I could not abstract away at the moment. But the application is pretty simple. It has one state, which is the initial count for the countdown, initialized with 0. And then it's listening on user actions that it received through a channel. So the application got the receiver side of a channel injected. And depending on the message it received, so here this is pattern matching in Rust, so it tries to see what was the message that came in, if it's a decrease message, increase message, or a start message. And then it's increasing, decreasing the count. And finally, after processing the event, it's printing it. But how can it print it? Also here I used dependency injection, so I have in the function signature I have a display variable of type D, and D is anything that implements the output interface that I have defined. So that's what I mean by the application doesn't know anything about the lower levels. Good. I think it makes sense to go back to this diagram. So we looked at the application code. We have seen how the application code gets called. Now we briefly look at the LED matrix, how it works, and how it interacts with Zephyr. So I told you this display variable implements the output trait that I have implemented. The trait is an interface in Rust. And this interface has only one function, print. And it takes a string as a parameter. Now, if we look at the concrete implementation of my LED matrix, we see it's a structure which holds a pointer to the device. And there are two functions on this LED matrix structure. There's a new function, which is a constructor. So when you basically create a LED matrix, it gets the device from Zephyr. So this is now a foreign function call. MB stands for microbit, I think, display get. Microbit is the board that I'm using. So this is getting an instance of the display. And this took me a little bit to find it, because actually there's a device driver for this display in Zephyr. So I didn't have to write this application which refreshes the 25 LEDs in a high frequency. So there's one existing already. So here in the constructor, I ask to get it, then I store it in my object, and later on, my application, let me switch over, can just call a print, the print function with a message, with some text, and the LED matrix will basically call again a foreign function, MB display print, with some parameters. This 1000 stands for the display duration for one letter, which is one second actually. But I have to do a little bit more. We are crossing language boundaries again. On the Rust side, when you work with strings, strings are encoded as a length and then the bytes of the string. There's no 0 at the end. Zephyr on the other side is C programming language. It expects 0 terminated strings. And there are different ways how I could convert this now. What I have done is I've chosen to allocate a buffer on the stack with 16 0 characters. Then I copy the string over from the caller into this buffer, put a 0 at the end of it, and then I call the display print function with the pointer. And this is some conversion I have to do if I don't want the application to know anything about using C strings. And I think that there should be a layer where we change this, and it should be always at the same level, so that you don't have some code that works with C strings, some with Rust strings, and so forth. Give you a second. There are at minimum 2 errors in this function that I didn't correct. I don't know if somebody sees them right now. I mean, I implemented it and also didn't see them at the beginning. One thing is, I allocate a buffer of 16 bytes. And I mean, Rust guarantees me memory safety, right? And so I allocate these 16 bytes, and then I copy basically number of bytes, so many bytes from the input string as the size of the input string is. And in my example, it's always less or equal to 10. But if somebody modifies my application, he writes a novel basically, or calls it with a novel, and then it prints out the novel, then it will not fit into this buffer. And there are some safety checks in Rust which are executed at runtime. So it will be detected, but what should the embedded application do? It will basically panic at the end. So this is still one problem that I have in this application. So I have to catch this first. And the other thing, which is more important, I told you that an unsafe block is just a marker for the Rust compiler, which tells the Rust compiler, here comes code that you don't have to check. I'm responsible as the developer for its correctness. And what I do is basically I put a pointer to this buffer into this function. And I have no idea what happens on the Zephyr side. Is the pointer saved somewhere and accessed now for the 10 seconds that the printout takes? Is the content copied? I have no idea. And even worse, I mean, the function returns immediately. And once I leave the print function, the stack is gone. So I don't have a complex application, so the stack doesn't get overwritten. But this could be still a problem that I have. So in my unsaved blocks, I have to be very, very careful what I do. So I have to review now the description of the Zephyr function. Maybe I have to look into the implementation, what it does to write safe code. So safe code basically means at least 4 eyes have to look at it to detect that everything is working fine. There was one problem that I had when I wanted to use this driver, which is actually it was not exposed to the Rust side. So first I had to go to the project configuration and configure in this kconfig syntax that I want to use this display driver from microbit. So it got enabled in Zephyr, but then the language bindings were still not available. At least I didn't see them. So I had to look basically how are the language bindings generated. And I had to look where is this pre-built step which passes all the Zephyr headers and decides which functions get exposed or not. And let me see if I can find this. Yep. Yeah, it's here. So in this Zephyr sys crate, this is basically doing this conversion step. We have here a configuration of the bindgen tool, which passes the headers and decides what gets converted in this bindings file and what not. And so I basically had only to add this entry here, allow list function, and say all functions starting with an MB underscore should also be available to the Rust application. Which was, I mean, once you know where this location is, you can do it. I don't know if this is the best way to do it. That's something I have to figure out. But now I'm able to use this device driver. And yeah, we're good in time. So we can also have a quick look at my keyboard monitor thread. Going back, the keyboard monitor. We have seen the receive side of a channel. Here the keyboard monitor gets injected the transmit side of the channel. So it's able to send, here in line 39, to send some events to the application. And we are now in this keyboard thread. We are basically taking the 2 buttons from the device tree. So they are configured in, let's have a quick look at the device tree of this board. You see these buttons, and there should be somewhere switch 0 and switch 1 here. So these are the aliases, and here are the buttons. So these are the configurations which say which GPIO basically is responsible for button A and which is responsible for button B. And thanks to this pre-build step for generating the device tree, I can now access them in my Rust source code. So I take an instance of these buttons, which are GPIOs. Then I configure these buttons as inputs. And then in an infinite loop again, which is a different thread, I ask for the current value or the current state of the GPIO. And then I use pattern matching to decide what I want to do. If the left button is pressed only, then I decrease the number. If the right button is pressed, I increase it. If both are pressed, I start the countdown. So this is the whole application now. I could also, instead of these buttons, use anything else. So I can attach a real keyboard if I would have a driver for it, and there would still, the business application wouldn't change. Pattern matching is also pretty cool for another reason, because if I don't have all cases covered, the compiler will yell at me and tell me, hey, I missed something. And this is also, again, pretty nice if you want to implement something. So one of the first applications that I implemented in Rust was a co-op library. And I took the standard and wrote it down, and there are a lot of switch statements in my C version. And once I ported it over to Rust, I identified some cases that I didn't cover, because in Rust, all your matches have to be comprehensive. They have to be complete. So this is my keyboard thread. But what makes this a thread? And this is, again, some benefit from the Zephyr crate. There are some macros defined. So here you see this function is augmented with an attribute that it is a thread. You can give it some parameters. For example, tell it how much bytes the stack should be. And then once you call this function, you get back a thread handle that you can start. And it's very easy to work with multiple threads here. Let's see if I covered everything. Yeah, I think I have shown you everything in the source code. So let's now prove that this is working. So to compile my application, I only have to do a west build and board name. I'm inside the project directory. That's why it's compiling this application. And I'm using basically the version that I got from Zephyr. So I know there are some commits which get rid of these warnings. But I left them in because I didn't want to use the latest version from mainline. I want to use basically what you get when you check out the Rust and Zephyr support. You see how much memory it's taking. I use a non-debug version. The debug version is almost twice in size. And then I can program it to my target with West Flash. And now it gets programmed at the moment. I mean, you don't see anything. And it's the same application that I had before, so it's not doing anything new. But the workflow is really, really simple. And I have a few years of embedded software developing now. And 20 years ago, it was a pain to set up the tooling, to set up the operating system and everything. And I think I can set this up in half an hour. And that's really great. So this is great tooling. Or if I want to debug it, I just say West debug, and then I have GDB available. So let me, these are some hints that you will find in the slides where I did some modifications. So as I said, enabling drivers, I had to go to the project conf, but I also had to change the bind chain configuration in the Zephyr sys crate in the build.rs. I was not showing exactly everything because the switches are not marked as GPIO LEDs in the device tree. They are marked as GPIO keys. So the device tree is not generating the wrapper code basically to access these GPIOs, but this is very simple. I just copied, it's the same. I just copied this section in the YAML file and renamed it to keys, and now I have access to the keys. Again, I don't know if this will be the best practice to do this because there's a lot of duplication. But this helped me to basically get also the different devices into my Rust code. And I had to learn from a pull request basically how to get language support in my IDE that also knows about the Zephyr crate, about the bindings files and so forth. So this is not mainline yet, if I'm correct. But if you do a symlink, your IDE, if it's NeoVim, if it's Visual Studio Code or whatever you're using, it's basically finding all the symbols that you want to use in your Rust application. And this was quite important for me. Otherwise, I don't have visual feedback if I have a typo in a function name or not. But what did I learn? I mean, Rust support is now there for application development. And I think it's, you can write any Rust application now. So the question is just what you want to use from Zephyr. If you have the functions already exposed or not, otherwise you have to reconfigure it. Today it involves a lot of unsafe code, and we have to abstract this unsafe code away and provide a safety barrier basically, or trust barrier, where you say, above this line I can write my code without needing to think about these memory safety issues. So that's why I introduced this abstraction layer, and basically the Zephyr crate is exactly that. It's just not, just didn't have everything that I needed now for my example. It definitely needs more drivers and abstractions. It's also, there are some, I think there's a to-do list or something for I2C, SPI, and so forth. So if there are volunteers that know what they're doing, they can help providing these abstractions so that everyone can use them. But there are also some challenges. And I think bindgen configuration can be quite difficult if you want to expose more complex things to the Rust world. I have not much experience with that, but I think, for example, that if I want to use the co-op client or co-op server in Rust, maybe it has data structures that are not so simple to transfer to Rust, or if I want to use MQTT clients and so forth. So is this really worth the effort, is the question? Because what I end up at the end is the C interface. On the other side, I can add the dependency of a MQTT implementation or of a co-op implementation as a cargo dependency. And then I can use the Rust native approach. But then I have the application again. So I have the support in Zephyr, I have it in Rust. So where's the line? I have to choose basically what provides most benefit to my application. Also, we want to avoid duplicating what is already there in Zephyr. We don't want to write the device drivers that we have in Zephyr now in Rust. We want to write an application that uses device drivers. So I think that's also a reason why we probably don't have the embedded hull there, because on top of the embedded hull, you build device drivers again. And in the previous project that I did where I had a temperature sensor, I mean, for my previous experiments without Zephyr, I had to have a driver for this temperature sensor. But now with Zephyr, I can use what is already in Zephyr, and that's a huge benefit for me. So this was more or less what I wanted to tell you about the support of Rust and Zephyr. I think you have to be careful at the moment because it's moving forward, hopefully. But I think it's fully functional to start writing your first non-trivial applications and closely monitor what's happening on the Zephyr side. And ideally, contribute. So, thank you. And I think we have a few minutes time until the next presentation. If you have any questions. Just check that we don't run into the next talk. So next talk is probably at 5 past. Is this right? So maybe one. That's the next talk. Okay. So maybe 2 questions. Yeah, Mohammed?
I noticed that in your example, you still non-terminated your string. Was that because you're passing it to the SQL queue?
Exactly, yeah. So this was the reason why I have here in my LED driver this code block here. And there are probably different ways to do this. It's just one idea, which I told you is not the best one because it's a local variable on the stack. And we don't know what's happening with this pointer in the print statement, yeah. So, yeah?
So it's a question on the same code then. So you can statically see that this will sort of rank when the string gets too long. But curious if the compiler, the Rust compiler, will complain or warn or freak out over this.
No.
It's a runtime.
Yeah, it's a runtime variant. No, the question. Yeah, the question is more if the compiler has a bigger context that he sees what are the passes coming in, and no, it doesn't. At least not yet. But a good static code analyzer should. I don't know yet how good the tooling here is. I mean, tools like Coverity for C. If there will be something which analyzes the software and the execution path, it should be able to find it. Yeah. I think we can have one more.
There you go. You have more time for questions, right? You can have. The next talk, I think, here is in 1 hour. So.
Okay, but still, people want to
5
go.
minutes, you have 5 minutes more for questions.
Yeah. So let's see.
So far you made built your main application in Rust,
Mm-hmm.
and then you use the wrappers which are exposed from the build system in Rust, but can you also call Rust code from the C part, like if you have UART driver and you want to use a library to like process the data, what you look into that, like from the other side.
Mm-hmm. So basically, I mean, callbacks are one way. So you could write, for example, an interrupt handler or something like that. I mean, there are two things that are important. One is what we have seen in the main function. You have to make sure that this symbol doesn't get mangled, so that the C code or that the linker finds the symbol when you call it from the C code. So the transition from C to Rust and from Rust to C is very, very simple, and it works quite nice. So this is important. So the no mangle extern C, so that the name is exactly in the as the linker would expect it when you call it from C. And the other thing, I just introduced the concept of interrupts. I mean, you have also basically to mark. I don't know how this is correctly done, but you have to also, if you want to have an interrupt handler, you have to mark it as an interrupt handler, because you don't want to have stack allocations and so forth in interrupt handler. As far as I remember, some years ago that I did interrupt handlers, but yeah. Does this answer your question? Yeah. Anything else? Yeah.
Rust is UTF-8, right? So Zephyr is ASCII. So I think your conversion goes wrong.
No, it could go wrong. Yeah, you're right. Absolutely. So 3 errors in this example. So what he was just bringing up was in Rust. In Rust, it is guaranteed that strings contain valid UTF-8. And if I call the length function here, it basically counts the number of symbols, UTF-8 symbols, and not the number of bytes. And is it bytes? Okay, so
There's nothing wrong with that aspect of the code.
yeah, but the comment was right. We also have to think about UTF-8, because that's also another nice feature about Rust. If you're interacting with the internet, or if you write some REST endpoints and so forth, this also prevents a couple of issues that can arise. Okay, so one more question, then yeah.
Would you say it's worth the effort, also from a security or safety perspective, to introduce Rust in your application when you now have not only write the application, but also these glue and layer code in between that is, as we see here, also affected by bugs, by language traversal problems and so on? Because I've also tried out the Rust, and for my feeling, it was a lot of unsafe, a lot of exactly positions which would be findable by my C compiler. But now I also mark that this is a section that I need to take care of. So what are your experiences with that when it gets into more complex applications?
So I don't have more complex applications at the moment, but I mean, but you're right. I think most of this stuff, especially if it's used in many places, should basically, from my point of view, go into the Zephyr crate. If it's common infrastructure. I'm not sure about the microbit driver, probably not, right? But this is exactly the point. There's a layer which has to be handled very, very carefully. And if this can be, let's call it infrastructure code that is reused in other projects, then more people should review it. It should go into the official version. That's my position on it. Yeah. David, did you want to add something?
The comment, the way I would describe it, in writing bindings between Rust and C is harder than writing C. Yeah, you do the same thing. The goal is to get that in a shared place and done once, so that it doesn't have to be done. And then, hopefully lots of eyes, audit that code to the bindings are correct, and now it's continuing adjustments. But we're at this intermediate stage where most of Zephyr doesn't have bindings. That's the challenge here.
Okay. Yeah. So I think we stop with questions here. I'm here for the next 2 days as well. So if I brought up some context, some concepts that you didn't understand and you would like to have more explanation, just approach me. And finally, I think I also want to thank David for all this Rust and Zephyr work. So he's the main contributor. Thank you. Thank you. I will put it up. I think normally I can upload the slides somewhere, and I will put basically the link to the GitHub repository into the slides, maybe today or tomorrow. Yeah. Okay. Thank you. Bye-bye.